This exercise asks us to find the volume of the solid bounded by the paraboloids z equals 3x squared plus 3y squared and z equals 4 minus x squared minus y squared. In order to do this, we're going to have to find the xy values that describe the intersection of these two surfaces. And once we know that, we are then going to have to figure out which surface is above and which one is below within that region. So let's first find the intersection. We do that, of course, by equating the two curves. If z equals this and z equals that, and both of those are true at the same time, then 3x squared plus 3y squared is equal to 4 minus x squared minus y squared. I think I misspoke earlier. I believe I said something about equating two curves. These are surfaces, of course. We're considering both of those equations describing surfaces to be true at the same time. So we'll set those equal to each other. A little bit of obvious algebraic rearrangement. Let's add those negative terms over, so we get 4x squared plus 4y squared equals 4. Dividing through by the constant that is in common gives us x squared plus y squared equals 1. The central unit circle. So that's nice. You know what that looks like. Well, very briefly and crudely sketch it without a lot of work here. We got that region there. Clearly not even caring to close that up. We don't need to be precise. This is just a rough schematic. If we think about what this means in 3 dimensions, we have this paraboloid z equals 3x squared plus 3y squared. So we'll have a rather steep upward pointing paraboloid. We have this one here that is 4 minus x squared minus y squared. So that will be a downward pointing paraboloid. And you see these will intersect along a circle. That is the circle directly above this circle in the xy plane. That would be down here. And the solid is inside of that. And from this diagram, you can see that the second equation, this one here, is above, and the first equation given is below. That's a little bit ambiguous just writing that. This is the surface that is below the solid. This is the surface that is above the solid. We have to be careful because it's the surface is above this one and below that one. So don't read that as part of the sentence. You know what? Let me call those top and bottom instead. Top, bottom. Okay. The solid is above this surface that describes the bottom of the thing, and the solid lies below this surface, which describes the top of the thing. Now, I did this largely, I figured out which is which pretty much graphically. But of course, you don't need pictures once you have this description, x squared plus y squared equals 1. As long as you recognize that that is a circle, you can take a point inside of there, such as the origin, and use that as a test point. When xy is the point 0, 0, you get z equals 0 here, and z equals 4 here. 4 is greater than 0, so you know that this is the upper surface, and that is the lower surface. Now, this is important because we want to describe, then, the difference between these things. So we need to take the, in order to find the volume, we need to know the difference in heights between the upper and lower. So we need to take the upper surface, 4 minus x squared minus y squared, and subtract the lower surface, 3x squared plus 3y squared. So we have 4 minus 4x squared minus 4y squared. So that's not too bad. If we were doing this in rectangular, we would then integrate this expression with dx and dy in some order or another. But given the domain here, rectangular is not the easiest way to do this. We could do it, right? We could take, for instance, x from -1 to 1, and y going from between negative and positive square root of 1 minus x squared, but that's a pain with radicals and all that mess. hopefully you recognize this is very easily described in polar. So we see that the volume in question would be, expressing this in polar now, actually let me do one more step. This is 4 minus 4 times the quantity x squared plus y squared, right? Once we know that we're doing this in polar, we are motivated to try to arrange things algebraically to get an x squared plus y squared structure whenever possible, because that means that we have 4 minus 4r squared, right? This is our polar expression of the integral that we're looking at, and that is our dr d theta. R, if you think about drawing segments or rays or whatever coming from the origin shooting outward, the upper bound on r is always that circle of radius 1, so r goes from 0 to 1. Theta, we have this full disk, not a portion of it, so we're going from 0 all the way around to 2 pi. Looking at this, we see that we have a separable integral here. Nothing in the inner integral depends on theta at all. So we can write this as the integral from 0 to 2 pi d theta times the integral from 0 to 1 of, and if we think about how we would integrate this, this is a polynomial, so we want to fully distribute this through and write it as a polynomial, so we get 4r minus 4r cubed dr. And now, let's move over pretty far, we didn't do that, let's just do this here. So we have the integral from 0 to 2 pi d theta. That is, yeah, I'll go ahead and do this here. We have theta from 0 to 2 pi. I would ordinarily skip that, but I think this might be the first one of these we've done, so I'll go ahead and write that here. Times, we are integrating dr, so we have 4r integrated will leave us at 2r squared. Minus, that's going to be an r to the 4th dividing, makes that just r to the 4th. This is looking pretty good, from 0 to 1. Theta, going from 0 to 2 pi, is 2 pi. Inside of here, plugging in 1 squared is 1, so we have 2. Then minus 1, and, minus 0 plus 0, blah, blah, blah. 2 minus 1 is 1. And we just have 2 pi. And taking a look at my notes here, that is indeed the correct result here. So the volume between those paraboloids happens to be precisely 2 pi. I was mumbling about possibly skipping this step here, because of course this is an integral d theta, that's a 1 d theta. Just like if this were a dx or whatever else, this is just going to be the length of that interval. Right? We have the interval from 0 to 2 pi, and that is 2 pi units long. Now it works out if you do integrating, you get your theta, and you take 2 pi minus 0, leaves you 2 pi. But when you do enough of these, perhaps you've seen enough in your past calculus classes to recognize this pattern. But if not yet, you will soon have done enough of these before this course is out that you'll be able to recognize that, oh, this is just going to be the length of that interval. You take the upper minus the lower, whatever that difference is, that's what we have here. 2 pi minus 0 is 2 pi. There we go. But yes, so this one, once we set it up, a lot of the initial work was work we would have to do no matter what, right? We have to find the boundary, we have to figure out which one is higher and lower, and subtract to find that difference. Once we've done all of that work, like I said, we could do this in rectangular, but you have these radicals involved. That tiny bit of extra work then to put this into polar gave us some expressions that were way simpler to evaluate than whatever we would have had to deal with involving all those square roots. And given that we have a pi as a result, I suspect that evaluating this in rectangular would probably involve a trigonometric substitution somewhere along the lines. Or at the very least ending up with something that is an inverse trig function. But probably a trig sub. So, this is much cleaner. But that's the basic idea. Look out for any places that you can more easily express something in a polar sense. Also, algebraically, look for ways that you can get a structure, especially if you already know you're changing to polar, look for a way that you can get a structure like x squared plus y squared, which you can then just wrap up and make r squared. If you happen to not notice this, let me go ahead and write this down here. We had 4 minus 4x squared minus 4y squared. Supposing you hadn't noticed that, and you were just doing your polar conversion, you could just substitute in directly, right? X is r cosine theta. Y is r sine theta. So you get 4r squared cosine squared theta minus 4r squared sine squared theta, and hopefully you would at least recognize that you can factor out that 4r squared. Sorry, it's a negative 4r squared, which when you factor out that negative 4r squared makes that a plus. And then this, of course, is 1, leaving you the 4 minus 4r squared, which, hopefully I've done that right, and that's the same as we got there. Yeah, 4 minus 4r squared. So you can still get to that. Or even if you don't, and you just have this thing right here to integrate. I mean, it works, but it's a whole lot more work, right? Just blindly plugging in what you know about x and y will get you where you need to go. But it is a whole lot easier if you are kind of actively looking for a way to find that x squared plus y squared structure. Because if you can algebraically get that, then you've got a nice quick replacement to get your r squared, and that saves a ton of work. So, be alert for such things as you work on these on your own.